when we started on lesson 2.1 and then 2.2, we talked about arithmetic sequences on lesson 2.1, and then we compared them to linear functions on lesson 2.2. What I want you to remember is that for an arithmetic sequence, our formula was AN equals AK plus D, where D is a common difference, times N minus K. That was your arithmetic sequence formula. Now this was that was your arithmetic. When we got to lesson 2.2, I said, hey, this is very similar to a linear function. In linear, we say the equation is y equals m x minus x1 plus y1. Now, if you really compare them closely, you'll see that both of them have some value multiplying a parenthesis. So the common difference and the slope are similar. These values are similar, the common difference and the slope. And then the y1 and the ak are similar. You can see how these values correspond to one another. That's how the relationship between these. Last thing, I didn't put that here, where your common difference, it's equal to taking any value from a sequence and subtracting the one that came before it. Taking any value of the sequence and subtracting the one that came before it. So whatever n is, whatever two values they give you, if n is 10, then this would be n minus 1, this would be a9. If you took a sub 10 and you subtracted a sub 9, you'd get your common difference. Okay, so I'll put that. Those were your two formulas that we had on that. Now, let's come on down here. Last thing, actually. Do you remember what's the difference, graphically speaking, between a sequence and a function? What's the difference between the sequence and a function? Do you remember? Okay, I'll tell you. A function is continuous, like this. Function is continuous, whereas the sequence itself is discrete data. It would be discrete, where that just means a bunch of dots along the line. So this one's discrete. This one is discrete. That just means a bunch of dots, whereas the linear function is continuous. That's the difference in them. In real world, things you count are discrete. Things that are measured are continuous. That's the difference. If it was a real world, if it were countable things, you'd say it's a sequence, discrete. If it's not countable, if it's measured, then it's continuous. Okay, finally, let's go to geometric. So in geometric, our formula was G sub n equals, do you remember? Without me telling you, do you remember what it was? Okay, times r to the power of n minus k, where r, so instead of having a common difference, we have a common ratio. It's where you take any term and you divide by the one that came before it. How is this similar to exponential? With exponential, the formula I gave you was y equals y1 times your base raised to the power of x minus x1. Once again, you can see that values correspond to one another. Your base and your common ratio, they correspond to each other. The GK and the Y1, they correspond to each other. You can see these values correspond. Okay, questions about those formulas? Just know your formulas. A lot of the problems, if you know your formula, are basic to solve. I'm going to use those formulas throughout the rest of this front slide. We're going to work through, I think it's just 3 problems. We'll use these formulas to help us as we go. All right, so let's try this first one. It says, determine the equation or rule for the following sequence. We have 3, 12, 48, 192. My question for you, it says it's a sequence. It says it's a sequence. Is this arithmetic or geometric? Geometric, good. How'd you know it's geometric? Because you see it's not adding by the same amount. It's like we would add 9 here, but this is not adding 9 there. So it's not arithmetic, so it's got to be geometric. If you want to find the ratio, the common ratio, Randy tells me it's 4. What you do is you take any term and you divide it by the one that came before it. So if I took 3 and 12, what is 12 divided by 3? 4. That's your common ratio. So I'm going to call this G1 here. This is G2. This would be G3, G4, and so on. If I use my formula, Gn equals Gk, which you can say, I'm going to, on this one, say my Gk is going to be equal to G1, which is, G1 is 3. It'll be 3 times 4 to the power of n minus, what's my k right here, just to be clear? K is 1, good. So it'd be n minus 1. That's where that comes from. That would be my formula right there. That's it. Just to be clear, mathematically, that is equivalent to, you could have plugged in a 12 right here and had a 12 but an n minus 2. Or you could have put a 48, n minus 3. Or you could have put 192 right there, n minus 4, and it would have worked. So all those formulas would have worked. That's just using exponential, manipulating your exponential functions by properties. Okay, how about the next one? It tells us this sequence is arithmetic. A3 is here, A32 is 228. So let's start this. Since I can't find a common difference, since they're not next to each other, I better use the formula from the get-go. What was my formula again? AN, AK, D times, there you go. Okay, that's your formula. What we're going to do here is to solve this, I'm going to start by saying AK is A3, and what is A3? Now if I do that, that means K is what value? 3, good. What I'm also going to have to do, since I don't know my common difference, is I'm going to have to say this is AN. I'm going to say for a moment AN is A32, which is 228. If A sub n is equal to A sub 32, that means n itself is going to be 32. So if we substitute these values in, we should be able to solve for a common difference. So instead of AN, what am I substituting for AN? What's the mathematical value? Nope. 228. 228 goes there. What's the mathematical value for AK? 25. We don't know D. That's what I need to solve for. I do know N. What am I substituting for N? And for K? 3. Now we can work through this and solve it. We're solving for our common difference here. I'm going to follow PEMDAS parentheses first. What is 32 minus 3? So 228 would equal 25 plus, you said that's 29. I'm going to rewrite this as 29D. How would you solve from there? Subtract 25 from both sides? So when I subtract 25 from both sides, 228 minus 25 is 203. So 203 would equal 29D. Arlene, I see you have a computer open. Do you happen to have a calculator available? Could you type in, sorry, I'm getting a step ahead. What do we do to get D isolated here? Divide, that's multiplying. Can you take 203 and divide that by 29? I'm guessing that's 7, but I'm not for sure. 203 divided by 29, it's 7? Okay, so if our common difference is 7, I'd like to say that's our answer. That's not the answer. This problem says determine the equation Now I can solve my equation. You plug it back in where you do not substitute an and n. So what I'm going to do is I'll take that to write my equation. I'm going to say it's an. This time I'm just going to, this was like a temporary value over here. The an is like your y, and n is like your x. So this is temporary what I did right there. What I'm going to do now is a general equation to solve for any n value no matter what. So it'd be an equals, what did we say ak was? 25 plus, what's our common difference? 7 times n minus 3. You could leave it like that. You could actually simplify if you wanted to. I'm kind of doing extra now. What could I do with this 7 in the parentheses? You distribute. You could say it's an equals 25 plus 7n minus 21. And you could actually combine those like terms and end up with the equation an equals, I'm going to put the n first. I like n first. 7n, what's 25 minus 21? 4. You could simplify this equation all the way to there if you wanted to. It's kind of the same idea on the previous problem when I told you you could do exponential properties, change this around if you wanted to. Like you could, when you have an exponent that's subtracting, you could, if you remember, divide the base. So you could just divide this by 4 to the power of 1 and get rid of that if you like. So those are things you don't have to do. I'll just write what I just said. You could rewrite this using the quotient property. Using the quotient property, what you could do is say that this is 3 divided by 4 to the first power times, whoops, forgot the 4, to the power of n. You could rewrite it this way. What is 4 to the first? Actually, I don't want anybody to get confused. I'm going to rewrite it one more time. Sorry. 4 to the first is just 4. You could rewrite it that way, and that you could finally rewrite as 3/4 times 4 to the power of n. You could write your equation that way if you wanted to. You could write it like that if you desired. So just to let you know, there's different ways you can write an equation, but as long as they're mathematically equal, you're good to go. Any questions on that? Okay, I'm going to do one more of this type before we move on to the next topic. So these were topics 2.1 and 2.2. We are testing over 2.1 through 2.8. So the front side is the first 2 lessons. All right. Determine the equation or rule for the following sequence characteristics. So this one doesn't tell us what type. It says A0 is 2, A2 is 1.28, A4 is this. What do you think, arithmetic or geometric? Are they subtracting the same amount each time? Is it subtracting the same amount?
No.
No. If it's not subtracting the same amount, then it must be a geometric sequence. It must be multiplying by some amount. Once again, since we don't know what we're multiplying by, and since these aren't back-to-back, I cannot discover what the ratio is because these numbers aren't back-to-back. What I'd have to do is use my formula. Gn equals gk times the ratio to the power of n minus k. So let's pick some points here. On this problem, what do you want to say gk is? I'm going to say it's this A0 there, which means that gk is equal to A0. A0 is 2, and k will be, what is k in our problem? 0. Good. I also have to find a gn. This is going to be temporary again. So gn is typically like your y, but to solve this, I'm going to have to do this. Gn can be either the other two. I'm going to just use A2. Gn will be A2, which is 1.28. Don't panic about me switching from this letter A to a G. G stands for geometric. A usually stands for arithmetic, but here it's just the sequence is given with the letter A. Okay, and let me put down n is 2. So if we substitute n, we can solve here. Gn. What are we substituting for Gn? 1.28 equals GK 2 times R to the power of, what's n? Minus, what's k? 0. To solve this problem, what's the opposite of multiplication? Divide. We divide both sides by 2. Anybody know what 1.28 divided by 2 is without a calculator? 0.64 is correct. 0.64 equals R to the power of, what's 2 minus 0? 2. Okay. 0.64 equals R squared. What's the opposite of a square? Square root. Square root. So technically, anytime you add a square root, you should add positive or negative anytime. I'm not going to stress over that, but do y'all know what the square root of positive 64 is? Square root of positive just 64. 8. Do you know what the square root of 0.64 is? 8. So technically it's did I say 8? Sorry, I meant to say 0.8. It could be the positive version, it could be the negative version. They don't tell us here, so I'm just going to go with the positive. Alright, I'm just going to go for the positive, the formula. Once you have this, we can plug in our values. You return Gn. So I'm no longer working with these temporary values. So I'm just going to say Gn equals, what was our GK again? 2 times the base of 0.8. I'll just do it in parentheses here so it doesn't get lost in the multiplication symbol. To the power of n minus 0. Do I need to put n minus 0? Just put n. Because it's n minus 0. That's our formula right there. All right. This deals with lesson 2-3. On 2-3, we learned about exponential functions, specifically growth and decay and properties like that. So it says, given the values a and b, determine if each is exponential growth or decay, and write a mathematical limit as x increases without bounds. So there's two things we have to do. So first, do you remember how to recognize if something is growth or decay? What do you look at if it's growth or decay? Less than or greater than 1. Which value? The A? No, not the A. The base. This base right here, would this be growth or decay? That base is decay. What about 5/2? That's because it's less than 1. Decay is less than 1. What about 5/2? Growth. 3/4? Decay. Okay. Pretty simple there. Now, graphing it, the A value is like your initial value. So, just really quickly, I'm going to do very basic drawings for each of these three. Very basic drawings here. Nothing special about them. The A value. What did I just tell you the A value represents? It's like your y1, your initial value. So go plot a point where you think on the first one, I'm going to say -3 is down here. That's -3. On this one, 8 would be up high. There's 8. And the last one, 2, would be somewhat low on the y-axis. So all those are like your y1 value. Now, if it's decay, what does that mean about your graph if it's decay? leaving. What does it mean if it's decay? Is it that it's leaving the asymptote or approaching the asymptote? Which one is it for decay? Approaching. Approaching. Hey, Daniel, can you close your computer for me? So you're not distracted. We are approaching. So the graph should look like this. Since this is decay, it should approach. Whoops. This should approach the horizontal asymptote like this. Decay approaches the horizontal asymptote. Okay, the next one. This one's growth. What does it mean if it's growth?
Leaving.
Leaving. So it starts on the asymptote and it leaves it. Okay, and this one, decay. What does decay mean again? Approaches. So it's going to hit this and get closer to that horizontal asymptote. So that's what my graphs would look like. To finish this off, it says write a mathematical limit as x increases without bound. As x increases without bound. Someone give me as a symbol, what does it mean for x to increase without bound as a symbol? X going to infinity. So in all these, we're going to talk about what happens as x goes to infinity. For this first one, I'm going to just call it f. I'm going to call this one f of x. We'll call the next one g and the next one h. What's happening as we go to the right, as x gets closer to infinity, as x gets bigger and bigger and bigger? What happens to the y values? Do they rise without bound, fall without bound, or get really flat?
Flat.
Flat. With what y value? 0. So that would be the answer to this one. It flattens out on 0 as x goes to the right. Okay, how about the second graph? I'm going to call this one g. What happens on this one as we increase without bound? As we go to the right, what happens to my graph? It rises to positive infinity. It increases without bound. Excuse me. Okay, last one. I'm going to call this one h of x. What happens to this one as we go to the right forever? Does it rise, fall, or get really flat? And what does it get flat on? The horizontal asymptote, which is 0 on this. 2-4. So on 2-4, we talked about the laws of exponents. There were 3 in particular. Before I start working these problems, just to help you out, what I would make sure I know if I were you is what happens with the x, which are like the exponents. The x, which are the exponents. The inputs are the exponents. And your y is your bases. If your, I want to mix them up here. What would it mean, what is true if your exponents are adding? What could you do to your bases if you did not want your exponents adding? What could you do instead? You could multiply your bases. Very good. Okay, what if you came to a problem and your bases were dividing, but you didn't want to do that?
Sure.
You could subtract your exponents. Okay. What if your bases were powered up? That would mean your exponents you could multiply. Okay, what if your exponents were dividing? You could power down, which is basically you take a root. I want to put that in parentheses. You take a root, like a square root, cube root, something like that, depending on what you're dividing by. Okay, I'm going to keep that up there so that you can see this play out. One of the things that's not on there is this: if you have a negative exponent. I should do this. I should add this on there. There's a rule for if you have a negative exponent. If you have a negative exponent, which one would exponent be? X or Y column? Okay, if you have a negative exponent, that is the same thing as taking the reciprocal of your base. What does reciprocal mean? Not opposite. What do you mean by opposite? Be more specific. Flip. That's what I'm looking for. Flip. So, first off, this problem. Notice, you see how I have a negative power? I have a negative exponent here. Negative exponent. What can you do with a negative exponent? I'll go ahead and write it out of the way. You can take the reciprocal of the, someone say it, reciprocal of what? The base. What's my base here? My base is 1/5. What's the reciprocal of 1/5? 5 over 1, or you could just put 5 to the power of 2x. Just to be clear here, where'd the negative go? It became the reciprocal of the base. The negative exponent is changed into the reciprocal of the base. Mathematically, that's the same on exponential functions. Okay, from here, what do you see is happening between the 2 and the x right there? Multiplying. What am I multiplying? I'm multiplying what right now? I'm multiplying exponents. What can I do if I'm multiplying exponents? Exponents. There you go. What can I do if I'm multiplying my exponents? Power up. So instead, I can take the 2 on the inside. So that means g of x is equal to 4 times, what is 5 divided by 1? 5. And you can do the squared there to the power x. What is 5 squared? All right, 25 is correct. So my final answer here would be it. It says to write it in this form right here. But it says to name it f of x here. Sorry. Use the law of exponents to write a function f of x in the form f of x equals a times b to the power of x, and f of x is equivalent to g of x. So I need to rename it f of x. I would say f of x equals 4 times 25 to the power of x. That's my equation right there. Does that make sense? Let's try another one here. On number 2 here, what do you notice is happening? So I need to have a times b to the power of x. Right now I have this. What's happening here? What's adding? Adding bases or adding exponents? Okay, if you're adding exponents, what's something else you could do mathematically? Multiply your bases. So here's how you would rewrite this. You'd say g of x equals, what's my base right now? 3. It would be 5 times this 3 to the power of x times base of 3. Notice I made a new base, 3 cubed. So check out what's multiplying. Am I multiplying my exponents? No, I am multiplying bases. But the way you would simplify this is you don't actually multiply these numbers to make it a 9 or anything like that. What I did is I just showed you it's multiplying by the same base. Now how you'd solve this is you need to know what 3 cubed is. Do you know what 3 cubed is? 27. Good. That's 3 times 3 times 3. That's why it's 27. So this is 5 times 3 to the power of x times 27. We're simplifying is all I'm doing right now. There's one more simplification I can do to get my answer. 5 times 27. Do y'all know what 5 times 27 is? Once again, it said to write the answer as f of x.
35.
135? That's some good math. 135 times 3 to the power of x. If you're wondering, wait, why did you drop the parenthesis? I'm writing it in the form it said up here. F of x, sorry, still not there. F of x equals a times b to the power of x. They don't put the multiplication there, but you need to when you plug in numbers. Mathematically, you need to have a multiplication there. It's 135 times 3 to the power of x. That's what this equation is equivalent to. You will not be given a graphing calculator on this type of problem, but if you checked it, this graph right here would be equivalent to this graph, even though the equations look totally different. That was what lesson 2.4 was all about, how to manipulate exponential functions. And 2.4 here. This is on your same slide. Sorry, I forgot. I made a second slide for myself, but for you, this is on the same slide of your packet. Let's try this one real quick. I'll put that little chart there. Okay, starting off on this one. There's a little order operations you have to have going on here. What do you see is happening when you look at this? There's a negative power, but to do this properly, you have to factor out the negative. So I'm going to first rewrite this like this. 4 to the power of, I'm going to rewrite that 1/2 as 1 over 2 that way. I'm going to factor out the negative. So if I GCF, that's what I'm doing, GCFing the negative. If I took the negative, this is now a positive x inside a parenthesis. What happens to the negative 1? It's a plus 1 as well. Okay, so now I've GCF the negative. So to start with this, we'll talk about the negative. That is a negative base or a negative exponent? Negative exponent. What do you do? What can you do if you have a negative exponent? Reciprocal of your base. So in the reciprocal of 2 over 1, of 1 over 2 is 2 over 1. How can I rewrite 2 over 1? Actually, I'll do it just for now, like that. Negative's gone. So the power now is just x plus 1. You don't need to keep the parentheses. Okay, now what? What do you see is happening this time? The exponents are adding. What can I do if I have exponents that are adding? If your exponents are adding, multiply your base. Okay, so g of x, the base right now, what's 2 divided by 1? 2. So it's the base of 2 to the power of x times the base of 2 to the power of 1, like that. Hey, where did the plus go? The adding, where did that go? It became the multiplying of the bases. So it's not like it's just we canceled it. We didn't cancel it. It transformed from an adding of an exponent to a multiplying of a base. Now this we could simplify. So it becomes 4 times 2 to the power of x times 2 to the first is just 2. If you combine these together, you'll have your solution. You can multiply the 4 and the 2. What is 4 times 2? 8 times 2 to the power of x. Once again, I remove the parenthesis just because that's the form they said to write the answer in. Be like this. Hey, I don't want you to forget this. This 8 is like your initial value. That means it would hit the y-axis at 8. That's where it hits the y-axis. Would this be growth or decay? Growth. All right. That's the end of lesson 2.4 review. 2.5, 2.6 for a moment. That's where we use calculator modeling. I'm going to do the calculator at the end of the packet. So 2.5 and 2.6, that's where we did the modeling with Desmos, where we did regressions and stuff like that. So 2.6 and 2.7 I have combined here. 2.7 was over this thing called composition of functions, where you see more than one function working together, as here. 2.8 was when we had inverse functions. And what does it mean to be an inverse? So the way I taught it in your lesson is I didn't use the word opposite the whole time. I did not use the word flip. I said switch. Switch x and y. Okay. So on yep. So if I'm finding g of f inverse, that's what that is, f inverse of 2. That's what we're looking for. G of f inverse of 2. How would you start this problem? Not everybody at once. I would start with the inside. Now, if this says f inverse of 2, you start with the inside. F inverse of 2. That could be rewritten as, now I want you to think, usually we would say like f of x equals 2. But that's not a true statement. What I just did, usually we would write this as f of x. This is f inverse. What place is this 2 in? Is it in the place of x or in the place of y right now? X. So what I wrote is actually true. This would become the y value. What we don't know is what it equals. This right here, this is saying the inverse value is actually the y value of f. So let me say it this way. The x of the inverse is equal to the y value of the regular function. Do I need to write that down? Okay. This right here, you're saying is the x value. Are you in agreement with me? That's the x value?
Yes.
Okay, here's what I'm saying. The x value of the inverse function is equal to the y value of the original function. The x value here in the inverse is equivalent to the y value. I need to put that this is now the y value. The y value of the original function. Are you tracking with that? So here's how I would solve this. If this right here, is this the inverse or is this the original function? Look right here at this symbol. Is this the original function or the inverse? This is the original function. That right there is the original. If the original function's y value is 2, you would look up here and to where y would equal 2. Y equals 2 on this spot right there. That's where y is equal to 2. So where does the graph, if that's where the graph hits, what's the x value there? That's a y value of 2. What's the x value? I hear 0. Okay. Here's what that means. If this value is 2, that equals 0. Or you could say, so you could write it f inverse of 2 equals 0. Or if you wanted to use this terminology, you could say f of 0 equals 2. Notice the only thing I switched is my inputs and outputs. And that's what happens on an inverse. Hey, Gabriel, make sure it's with me, please. We're just switching inputs and outputs on an inverse. So, saying all that, what is f inverse of 2 equal to? 0. So how do I continue on? I take this value and I substitute it in. Now I'm looking for g of 0. So g of 0, you would take this equation. And if I'm plugging in a 0 here, I plug in a 0 there as well. 0 minus 4. Okay. What is 0 minus 4? 6 over negative 4. And that can reduce. What number goes into both of those? 2 goes into 6 how many times? 3. And 2 goes into negative 4? Negative 2 times. So that means that, just to tie it all together, g of f inverse of 2, which you could rewrite as g of f inverse of 2, is equal to negative 3 divided by 2. Now that's less than 2.7 and 2.8 combined. The inverse right there is less than 2.8. Doing the composition, that's 2.7. Remember, composition means you solve the inside first, and whatever solution you come up with, you plug into the second function, the outside function next. And you simplify to get your answer there. Notice, you know what value I never use as part of my answer? 0. But that was just the bridge value that got me from f inverse to the function g's input. So that was a bridge value, but I did not include it in the answer. That 0 is just a temporary value. Okay, I have 3 of these, I believe, for you. So let's try the next one. Is it only 2?
Yeah.
3 in total. I got 2 more. 3 in total. Okay, the next one. Okay, let's look for this. How would you begin this time? Oh, I got a typo here. I should have a third parenthesis right there. I hear 7 into G. I totally agree. This happens first. 7 goes into G. So let's start with there. G of 7. If I'm plugging G into 7, do I look at the graph or do I look at the equation? Equation. I plug it in there. So it's 6 over 7 minus 4.
6 over 7.
Ooh. 7 minus 4 is 3. And what is 6 divided by 3? Okay, so if G of 7 equals 2, what do I now do? Plug that into G. So if G of 7 is 2, I'm now going to plug that into this G. So now I'm going to G of 2. I think the way I did it before is I was using arrows. When I showed you the first time, I did it this way. I said, okay, if 7 went into this G, G produced 2. And so now this 2 is going to go into this G. So let's see what G of 2 is. It's 6 over 2 minus 4. What is 2 minus 4? Negative 2. So it's 6 divided by negative 2, which is negative 3. So we plug that in and we got a negative 3. What do I do with this negative 3? You plug it into F. That's correct. Negative 3 is going to go into F. So is this an X value or Y value? X value. So I look on this graph. Negative 1, negative 2. Here's negative 3 right there. The graph's there. Oh, we're going to have to approximate. We don't have an exact value. Whoops, that's not good. Okay, well, let's approximate. What Y value do you get there? Approximately. Negative, positive. Negative or positive? You want to say negative 1.8? Okay, since I'm approximating, I'm going to do the squiggly. Negative 1.8. So what does that mean? That means our answer for the composition of F of G of 7 is equal to F of G of 7 with 3 parentheses, which is approximately negative 1.8. One more time, notice, did I include in my answer this intermediate value of 2? Did that get listed as part of the answer?
No.
No, and actually I didn't ever even use this 7 after the start. I used it one time and it was gone. Then I used the intermediate value of 2. It was gone. Then I used the intermediate value of negative 3 and it was gone. And then I took the final answer of negative 1.8. Okay, I have one more. Let's try it one more time. Go ahead. Camilla, sit up for me, please. All right, last one here. F of F inverse of G of 1. How do I start? Once again, I should have had a third parenthesis there, so sneak that in. I first plug 1 into G. So we start with G of 1, which is 6 over 1 minus 4. What is 1 minus 4? So it's 6 divided by negative 3, which is negative 2. What do I do with this negative 2? You plug it into F inverse. So F inverse of negative 2. Now, if it's F inverse, let's think about this for a second. What value actually is that when it concerns y? If that's F inverse, what is that when it comes to F? Is that the x value or the y value? This input is the output on the original. This is on the inverse, it's an input. On the original, then it's a output because you switch inputs and outputs on inverses. So when you do an inverse like that, you switch what's an input, what's an output. Gabriel, stay with me, please. And so I'm looking for, wait, are you saying that's an x value or y value then? That's a y value. So here's -2 on the y. That means I'm looking for where this intersects here. That's where y equals -2. It hits the graph approximately right there. What is approximately that y value, or x value, I'm sorry. -1, -2, -3, negative, what do y'all want to guess? -3 point what? It's negative, it's more than -3.5. 3.8? Okay, let's say that value is approximately -3.8. So what do I do with that 3.8? -3.8? You plug it into f. So now I'm looking for f of -3.8. So when I plug this in, now is this an x value or y value? X. When I plug in a -3.8, what does it produce? -2. Notice you don't have to approximate this time because it's the same value. That means that f of f inverse of g of 1 is equal to f of f inverse of g of 1, which equals -2. That was lesson 2.7 and 2.8. Lesson 2.7 and 2.8. 3 slides. This is going to be a 4-part problem over the next 3 slides. This is a bunch of the lessons combined here. So the first part is dealing with lesson 2.8, inverse. It says, determine if the inverse of f is a function. Give a reason for your answer. So let's talk about what this would look like as a graph. What type of equation is this? Like, is it polynomial, rational, exponential? Those are the equations you learn. Exponential. Would this be exponential growth or decay? It would be exponential growth. Why is it exponential growth? Because the base is greater than 1. Okay, normally I'd say this is the initial value at 0.5. There's one problem with this. We have transformations. Which way would I actually move this? Hey, stay with me. Which way would I move this if it was x minus 2? Right 2 units. So we would go right 2. I'm just going to say right 2. And then what would I do with this? Down 3. So this graph would have an initial value right there. And you said this is growth or decay? Growth. So what does it mean if it's growth? Normally, if it's growth, does it leave the asymptote or approach the asymptote? Leaves. It normally would look like this, but since I shifted it, it would now look like that. There's your graph. Okay, first question. Would the inverse of f exist? Would this have an inverse function, yes or no?
Maybe.
There was a test I gave you when you think about a graph to know if its inverse exists or not. What was the test?
The line test?
Yeah, what type of line test? Vertical tells you if the one you're looking at is a function. Vertical tells you if f's a function. How do you know about its inverse?
Horizontal.
Horizontal. Would this pass or fail the horizontal line test? Pass is HLT. Okay, now listen very, very carefully. Your reasoning for AP Pre-Calc, they do not accept passes HLT. They do not accept that as an answer. Now, I'm going to write it first. How do we know if it is or it does not have a function? It does because, here's what I'm going to write for us. That means f inverse exists. Why? Since f passes what test? The horizontal line test. Now that doesn't count for points. I'm just writing that down so I know what to write. Here's how you're going to write your answer. If it passes, it only passes because the graph is either always increasing or always decreasing. On this one, does the graph always increase or always decrease? Increase. So here's how you would write your answer. The inverse of f is a function since f is increasing on its domain. So number one, since it's increasing on its domain, since each input is increasing on its domain, each output is mapped to exactly one. I think that's the words they use. Exactly one input value. The inverse of f is a function since f is increasing on its domain, and I should say, and each output is mapped to exactly one input value. That's how you describe the horizontal line test. Each output is mapped to exactly one input. I'm going to explain this to you real quick. Everybody hold out your hand like an horizontal line. This is a test of outputs. I'll show you why. Outputs is like the y-axis. If you move this line up and down, what are you changing? Are you changing x's or y's? Y's. A horizontal line, believe it or not, tests y values. And so what we're saying here is since f is increasing, since it's going up, your horizontal line never hits the graph more than one place because it's always increasing. Now if the graph increased and decreased, at some point in time your line would hit the graph twice. This is the explanation they want to give you credit. If you want credit, you have to have this explanation. You can't just say this. Now that's what we're describing. This does exist since f passes the HLT. So how do you properly describe it to where they give you credit? You describe it like that. The inverse of f is a function since f is increasing on its domain, and each output is mapped to exactly one input value. That's the HLT right there. That's how you would write that. Now let's go to part 2. I told you this is a 4-part question. On your next slide, we have part 2 and 3 on your next slide. I'm going to copy the graph because I think I'm going to need it on the next slide. I can't remember, but let's check it. Part 2 says find the zeros of f if they, that's supposed to say they, exist. Write your answers as a decimal approximation. Okay, does this have a 0? What does it mean to be a 0? What, class? What does it mean to be a 0? X-intercept. Does this have an x-intercept?
Yeah.
Okay, we will have 1, 0. To find it, we would need the calculator, so open up your calculators. Let's graph it. It should be pretty simple to find if you just type in your equation. I think on the powers you have to put it in parentheses to make the x minus 2 stay in there. If you don't use a parenthesis on the powers, it always leaves the exponent. So make sure you put a power on that to make it work. How many decimals are required for AP Pre-Cal? 3. A 0 you write as x equals. So we need 3 decimals. I'm going to do the approximately symbol. 4 point, would it be 584 or 585? 585. That's my 0. Okay? And number 3. For you, this on the same slide. Just determine the equations of any asymptotes. So we do have an asymptote here. The asymptote is what this graph left. The question is, what value did the graph leave? Normally our asymptote is the y-axis, but this has been shifted down 3. So what value are we leaving? Should be a -3. Test it. Type in y equals -3. Does that look like an asymptote? Does that look like the graphs are holding hands together? Yeah, that would be my asymptote. That's not what I wanted to hit. I wanted to hit this one. Sorry. Let me do it as a dash so you can kind of see in between. You can see those graphs are following each other. It is y equals -3. Determine the equations of any asymptotes. I have a horizontal asymptote. That's what that is, horizontal asymptote. Of y equals -3. That's what that value right there did. That was a vertical shift. Shifted it down 3 from the x-axis. And finally, the last part to this problem. So that right there was less than 2-3, that portion. I didn't tell you. This portion right here, we didn't really talk about that with it, so I don't know what to call that one. But number 4, let's use limits to describe our end behavior. We have 2 end behaviors here, as you go left and as you go right. We want to talk about what's happening to the function f as we go to the right, and what's happening to function f as we go to the left. That's what it means to be end behavior. What's happening as you go left, and what's happening as you go to the right. Let's start with as we go to the right. What's happening to this graph as we go to the right? Is it rising, falling, or getting flat? Rising. If you're rising, what value is it approaching? Infinity. Okay, over here. Is this rising, falling, or getting flat? What value is it getting flat on? Yeah, -3. We just got that right there. -3. So that would be my 2 end behaviors for that equation. We talked about our limits on less than 2-3 as well. Right. Look at some stuff for less than 2-5 and 2-6, calculator problems. It says here the table gives the number of alternative fuel vehicles. I don't know why it's blurry. Let me try that. There you go. And thousands sold per year from 1996 to 2010. Find an exponential model. A of t equals a times b to the power of t, where a of t represents the number of alternative fuel vehicles and thousands sold t years since 1990. The first thing I would do here, when it says t years since 1990, what that means is our years isn't actually what we type in the calculator. How many years is 1996 since 1990? 6. So we're going to type in 6, 8, 10, 12, 14, 16, 18, and 20. That's what we're going to actually type in there. So let's open up our Desmos. I'm going to add a table. We'll type these in. 6, 8, 10, 12, 14, 16, 18, and 20. All right. It told us to find the exponential model. So when you type this in, the 2 things I would recommend you do, number 1, zoom fit it. Zoom fit your data. That shows you the actual scatter plot. And then do the regression. It said an exponential regression. So choose exponential. I'm getting a this equation 0.9928 as my r squared. Are you all getting the same values? Make sure I didn't type anything wrong. Is that a good value or bad value?
It's a good value.
It's really good. What's a perfect value? 1. So yeah, this is really good right there. Okay. Too small. So my equation we're going to be using here is a of t equals, we need 3 decimals. 152 point, which 573 or 574?
574.
573 actually.
Oh yeah.
Times the base of 1.095 to the power of x. That's what your answer would be for number 1 on this slide. Number 2, does the residual plot indicate the exponential model is appropriate? Why or why not? Let's talk about residuals. So to do a residual on your graph, do y'all remember how to do a residual? Down here you hit the plot button. You hit the plot, and then after you hit the plot, do a zoom fit on the residuals. So it zooms in right there. Is this good or bad? Appropriate or not appropriate? It is appropriate. Why is it appropriate? What'd you say? No pattern. That's right. It's appropriate since there is no distinct pattern. Sorry, I got to try to fit this in there. Little area. This is appropriate since the residual plot has no distinct pattern. Should say appropriate model. Okay. It says, what's the residual when t equals 10? Is this an overestimate or underestimate? So t equals 10. How do you know where t equals 10 is? You click them until you see, is t the x or the y? X. You go until you see an x of 10. There it is. On that point right there. Is that an overestimate or underestimate? Now, help me out. What's the estimate? Is the point the estimate or is the point the actual? The actual. You want to know about the estimate. The line is the estimate. Okay, so we're looking at this point right here. That's the point we're looking at. Here's the estimate. Is the estimate under or over the actual? The estimate is under. So we have an underestimate.
But that is above too.
The actual is above. The estimate is under. The estimate is under. Underestimate of 15.527. I don't know what these units are. Is it thousands of vehicles? Is that what it was? What was the Y value originally? Alternative fuel vehicles. Underestimate of 15.527. Alternative fuel vehicles sold. So that's the Y was representing the alternative fuel. I need a hyphen in there. It's an underestimate. Questions over this problem? No? One more time to look at a problem that would be going over using calculator. An ecologist began studying a certain type of plant species in wetlands area in 2013. In 2015, that's when T is 2, there were 59 plants. In 2021, that's when T is 8, there were 118 plants. The number of plants in this species can be modeled by a function P given by this, where P is the number of plants during year T and T is the number of plants since 2013. It says first, use the given data to write two equations that can be used to find the values for a and b in the expression for p of t. Okay, first thing you have to do is plug in your 2 points. They gave us a point right here. This is a point when t is 2, or x. When our input is 2, our output is 59. Our other data point they gave us is right here. They tell us when the input is 8, our output is 118. How do I write two equations out of that? Remember, P of t is equal to, it says it right here, a times b to the power of t. So how do I write two equations? Hey, stay with me, please. How do I write two equations? What do I do first? On this point, which one's the number of plants? P of t means plants. 59. So 59 would equal, we don't know A, we don't know B, but we do know T. How much time for 59 plants? 2. That's one equation. The second equation, how many plants are there right here? 118 equals A times B to the power of 8 is our time. So on this type of free response question, that first one is the only part you don't need a calculator for. Everything else you do. So part 2 says find the values of A and B. We don't actually have to do any crazy math. You can use your calculator. Let's do that now. So I'm going to plug in my points. I'm going to add a table. I'll type these in. My input's 2. My first input's 2. My first output was 59. My second input was 8. My second output was 118. I'm going to do a zoom fit. Regression. What type of equation is this right here?
It's
Is that linear? No. What type is it? Exponential. Go to exponential. There's our equation right there. Oh, man. Okay, there's my equation. It does not ask for the equation, it asks for the values of A and B. How many decimals do you need? 3. So A is approximately 46.828 or 829? 828, and B is approximately 1.112 or 123? 122. I think I said that wrong, but you got it. There they are. That's the second point here. This is the first point right there. Those would be your solutions. Okay, on part B. Part B has to do with the A-rock. So on this type of free response, part B will deal with the A-rock. Okay. It says use the data to find the average rate of change in the number of plants from 2 to 8 years. Express your answer as a decimal approximation. Show the computations that lead to your answer. You have to show your work, but here's a way you can get this. We talked about this. I think it was in your class. We talked about this. The way I've thought of how you can do this, first with the calculator, make sure you get it right. Number 1, you make sure you're only using the 2 data points they want. They want a time of 2 and a time of 8. Those are the only 2 we have, so we're good there. Go up to this edit list, and I want you to copy your data. Hit edit list, hit copy, duplicate. Everybody good there? Now secondly, what I'm going to do while I'm on edit is I'm going to hit the black. I want to have a different color. I'm just going to choose red. So I'm going to have a different color. Now A-rock does not look like exponential, ever. A-rock never looks like exponential. What does A-rock actually look like? Linear. Choose linear. So at this stage, you should have 2 regressions going. Does everybody have 2 regressions going? Okay, the linear, if you remember, your A-rock is your slope. Is everybody's slope the same as mine? 9.833. Is everybody getting that slope? Okay, I have to show the work, but that right there is going to be my solution. I better get that as a solution or else I did my math wrong. Whoops. If I don't get that as a solution, I did my math wrong. So let's make sure we do our math right. That's the number I'm looking for. So what is the formula for AROC? It's the change of y divided by the change of x. Okay, I'm going to slide this over so you can see. What were my original y values? 118, so it's 118 minus 59 over my 8 minus 2. Now that we can type in the calculator, that shows our work. We should get this value right there. We should get 9.833. That's what we should get. Now I'm going to type it in just to make sure I get this point. I want to make sure I did my work right. Let's just type it in and see if we get the same value. 118 minus 59 divided by 8 minus 2. Yes, I'm getting the same value. That's good news. So there's our first point. And I'm going to go ahead and put over here for the sake of notes that this was a linear regression. Because AROC is a linear regression. Okay, now it says, use the average rate of change found in I to estimate the number of plants for t equals 10 years. Show the work that leads to your answer. Well, we know what the equation is. This is the equation right there. Now, if that's my AROC, how to show my work, how could I show my work to get my answer? Where would I plug this 10 in? Is that an X or a Y? The X. So really, the work I would need to show is Y would equal 9.833, I'm going to round here, times 10 plus 39.333. I'm rounding off. Now over here, you don't actually have to type all that in. You could just simply type in X equals 10. Now, which intersection am I looking at? The red or the blue, the black? The red. Why the red one? Because this is the AROC, the other one is the exponential model. So that's my answer right there. Is everybody cool with what I'm doing so far? Whoops, 137.667. So can you have that many plants? Can you have a decimal of plants? So I would actually write the answer here of approximately 138 plants for t equals 10 years. Okay, so I would actually write that for my answer, just because you can't have a decimal of a plant. So that should make sense. Okay, it says the average rate of change found in I can be used to estimate the number of plants for t when t is greater than 10 years. Are these estimates found using the average rate of change less than or greater than the number of plants predicted by the model P for year t for year 10 t greater than 10 years? Okay, so I want you to explain it to me from this. Here's t equals 10 years. It said, hey, if we looked for t being greater than 10 years, which side of the graph we looked on? Left, right, top, or bottom? If t is greater than 10 years, we're looking on the right side. Which one's greater? The exponential model or the AROC linear model? The exponential is greater. So I'm going to write my answers. Are these estimates found the average rate of change? Okay, that's the average rate of change first. So how is this, the average rate of change compared to the exponential? Is the average rate of change less than or greater than the exponential? Less than. So I would write about this one because that's what it said. Are these estimates found using the average rate of change? I'm going to say, why did it do that? Sorry, let me delete this, delete that. Okay, here we go. The estimates found using the average rate of change. I'm just copying this right here. Did you say it's less than or greater than the exponential model? Is less than the exponential, or excuse me, less than what it said, the number of plants predicted by the model P during year T for T greater than 10 years. Now it says explain your reasoning. The reasoning you always say is about the concavity. Is this less than because this graph, is this less than because the model is concave up or concave down? What is going on with the black model here? Okay, it's less than. So I'll just add that in here. Since the model P is concave up. For, I don't know if you'd have to say this, but I'll just do it again. For T greater than 10 years. Is that it?